You want me to repeat it again? Any topic? Is there any topic you want to repeat again? Embedded system portion, not microcontroller. 8051 getting will do separately. Process and task. Delay. After process and task, we saw hardware software partitioning. Mush. Okay, let's look at the architecture of embedded system. And this one. Design methodology, okay. Delay. What else? Okay, let's look at the architecture first. Okay. So architecture again, I had uploaded the note. It's around 3-4 pages. Okay. So this really explains about real-time embedded system. Okay. Real-time here means that you can monitor instantly. Okay, you can monitor anything instantly, with prompt action. That's why there's a real time here. And whatever task you do, that is time bound. Okay, that has a starting time and there is an end time. It's not like unlimited time. It's not like infinite. There is a certain time, so it is always time bound. Okay, so there are as many architectures. So there are many ways to explain the architecture. Okay, delay. Okay, so always whenever you talk about embedded system, always remember there is two components. One is hardware components, one is software components. Always. Okay. So first you need to understand what are hardware components, what are the software components, and why this hardware and software need to be together. Okay. And the reason for this hardware and software to be together, I gave you 1 hour class that I don't know when onwards which day, but this is also called as hardware software co-design. Okay, please go through this. Okay, this whole paragraph, then you will understand. Always see. Let's read it through once. Both the hardware and software coexist in a coherent manner. Both the hardware and software need to be coexistence to each other. Okay, they need to be together. Okay, tasks which can be both carried out by hardware and software affect the design of the process. See, some tasks might be done by hardware only, some tasks might be done by software only. Okay, this affects the design of the system. Are you getting or not? For example, they have also given an example here. Please see this. Multiplication action may be done by hardware or it can be done by software by repeated additions. Okay. Hardware-based multiplication improves speed at the cost of increased complexity of the arithmetic. On the other hand, software multiplication is slower, but ALU is simpler to design. Okay, so what it does is hardware increases the speed of whatever operation you are doing, but software makes the things simpler. Okay, in this particular application, may not all application, in this particular application. So there are advantages of both hardware, using hardware, and also there are advantages when we are using software. Okay, so both the advantages of hardware and software need to be embedded inside. That's why we're calling this as embedded system. All the components embedded together. On the other hand, okay, software. There are some conflicting requirements which need to be resolved on the requirements as imposed by the overall system. So there are some constraints. Although there will always be constraints. Constraint means, okay, there will be some trade-off. Okay, and I have more explanation in the other note about this hardware software co-design. Please see this. Okay, that's why optimization comes into the scene actually, because some part of the hardware, some part of the software need to be optimized to each other. Okay, so that's why this all those algorithms, all those different types of heuristic algorithm law, all those algorithms, even a tree algorithm, all those algorithm came in order to optimize this hardware software co-design. Okay, so when we are talking about software, okay, when we are talking about software, software only deals with coding program. Okay, see, some of these parts may be programmable, therefore must have some place to keep these programs. So we need to have a place where the programs are kept. That's why we have memory, right? On-chip memory, off-chip memory. So in real-time embedded system, on-chip or onboard non-volatile memory does keep these programs. These programs are part of real-time operating system and continually run as long as gadget is receiving power. Okay. A part of the real-time operating system also executes itself in the standby mode while taking a very little power from the battery. This is called as sleep mode. Okay. This part we have not studied that much, but just understand that. Okay. Just understand. In order to have, okay, firstly, programs make softwares. Okay, programs make softwares. Software we need in embedded system. So we need a memory where these programs are saved. That's why those on-chip memory, off-chip memory came. Now, there are these special types of registers like Picon register. We have not studied this. These registers also helps in the efficiency utilization of power. If the embedded system is not used, the whole system should sleep that time. The power should not be used. Or the idle mode, sleep mode, idle mode, say. Okay, so we'll study that in the next class. Picon register, that is Picon register. But there are these facilities, okay, there are these registers which deals with efficient utilization of power. Okay, whenever we don't use, it need to be sleep or it need to be in idle mode. So all these things comes under software. Hardware, what is hardware? Okay, any system, okay, each system may be, for the segregation, it's small, may consist of some discrete part. So hardware is some discrete parts. Discrete parts means it is easily noticeable. Okay, when you open the computer, okay, you see the bus, you see the ASIC, you see the motherboard. These are discrete parts. Discrete part means it is easily differentiable, you know. Okay, there is a hardware, there is a big chunk of one block is there, this is a hardware. But usually softwares you will not see. Softwares are inside this hardware actually. Are you getting or not? So hardwares are discrete parts, they are easily differentiated, but software not possible. Okay, let's continue from here. Let us treat both hardware Let us treat both hardware and imbibed software in the same spirit and treat them as system. Later on, we shall know where to put them together. Thus, we can now draw hierarchical block diagram. Okay, now hardware has one separate importance. Software will have some importance, but both need to be together. That's why imbibed both need to be coexistent to each other. That's why this optimization came into the scene. Okay, are you getting or not? So that all these things together need to be designed in such a way that both the hardware and software will be used. Okay, in other than hardware and software, the connection between them, okay, between hardware and software connection, the connection between them is done by interface. Interface. Okay, can see this diagram. See, key interface, whatever interface you are seeing here, this is the standard switch connects hardware and software. Okay, are you getting or not? When a system is assembled, it starts with some chassis or a single subsystem. Subsequently, subsystems are added onto it to make it a complete system. See? So different subsystem will be subsequently added to each other with the help of interface, and they are formed. A complete system is formed. Are you getting? What are these examples of this is another important diagram. Okay, this solid line, whatever solid line you can see, these are all hardwares. Whatever dotted line you can see, these are all software components. Each has its own function. See, function MA, each of these component block key, and you can't miss. Like for example, ASIC. What does ASIC do? ASIC stands for application specific integrated circuit, for specific functions like motor control, data modulation, etc. Okay, motor control. So each of these block will have its function. These functions are written here. Please see this through. Okay, codec. See, codec. It's a very important codec. Compressor and decompressor of the data. To compress the data, to decompress the data. Sometimes the data won't be in the same size, won't transmit it in the same size. It needs to be compressed. Okay. Have you seen this when you have opened the computer? Ani, this part. This is called as SMPS. It's a very important component. Is it here? SMPS. No, it's not here. SMPS. What is the function of SMPS? It gives regular power supply to the motherboard. Okay. Let's start from here. Let us take the example of a desktop computer. Okay. Though not an embedded system, it can give us a nice example of assembling a system from its subsystem. So, your computer system is an assembled system, Imade. Why it is an assembled system? Because it is an assembling of many components, assembling of many subsystems like SMPS, motherboard, hard disk, graphic card, Ethernet card, all those. See, starting from chassis, SMPS, motherboard, hard disk, CD-ROM, graphic card, Ethernet, all these are subsystems which are assembled together and a desktop computer is formed. This is how exactly an embedded system is to you. Each of these subsystem consists of several components. Example, ASIC, microprocessor, analog. Inside this, all these components, each of these subsystem might have each of, like for example, SMPS, NASE, all these ASIC, microprocessor, analog. Each in CD-ROM, for example, in a graphic card, let's say, in a graphic card, all these components should be there. In SMPS, all these components should be there. Okay, that's why embedded system is the assembling of components. Okay, now Analu, okay. Each of these subsystems consists of several components. Example, ASIC, microprocessor, analog, miniature motor, multi-level supply units, crystal clock generator, surface mounted, all these things are there. Without this, computer will not work. Each of this assembled part of computer will have these parts. Then we are calling this as computers. Ani, this whole diagram, this whole components, all components in the computer, that might be many, Ani, this same thing. This whole thing making one component, one assembled part, one subsystem, and another one making another subsystem. All this subsystem connects together and makes an embedded system. Desktop computer will have more open standards than an embedded system. Please see the differences between them. Okay, this is because open standards. What is this open standards? This is because of the level of integration in the latter. Many of the components, open standard means whenever you open it, it's directly visible. But embedded system is not actually usually visible. Okay. Many of the components of the system are integrated into the single chip. This concept is known as system on chip. Thus, there are only few subsystems left to be connected. All these things, it's actually in the chip. It is not visible to you. Okay. Digital signal processor. There is no separate component as digital signal processor. It is inside the chip. Are you getting or not? Microcontroller is itself a chip. Codec. There is no separate hardware like called as codec. It is all inside one chip. All these chips are inside, kept in a PCB board. That is called as motherboard. Are you getting? That is called as system on chip. Not motherboard, system on chip. This system on chip might be inside SMPS, might be inside CD-ROM, might be inside hard disk drive, might be inside interface cable, might be inside motherboard, and making one full computer system. Okay, are you getting? So see, there are more than one microprocessor, 2 DSP are employed. See, in one microprocessor chip, one DSP, one microcontroller employed here to carry out different tasks. See? All these things, please go through, okay? Basic. And you need to remember all these functions, man. Each of these functions. Each of these functions. This is it for your architecture of embedded system. Any doubt?
No, sir.
Next, we'll go to design methodologies. Design methodologies. The engine is asking. Just a revision. Today we'll not go new topic, man. We'll see in the next class new topic. Okay, yeah, design methodologies. So design methodologies, why we have to focus in design methodologies is because we need to make our goals in line with the performance, function and power first. Okay. These three. Power efficient, performance in terms of performance, and it need to be function efficiently. It need to function efficiently. Again, these three things need to take care of these three things. What are these three? Time in the market, design cost, quality. What is this time to market? Time to market is, like for example, let's say a customer comes and asks you, okay, within this time I need to complete this function, need to complete this task. Say, Lavachin, that is time. Any task you do, it is time bound. Okay? Embedded system is running with some task. That task need to be within a time. Time bound. Not only time, it need to take care about cost. I need to make that system in as less as possible. All these studies they do and they design actually. And also quality. Okay. So how do we do this? There are these four methods. Okay. There are these four methods. One of the most popular is this waterfall model actually. I was working yesterday also in my project, waterfall model. Waterfall model where there are first. Okay, so actually, yeah. Whenever we are talking about these four models, just imagine that you have a project. Okay, you have a final year project, final semester project, and how you are going to do that final year project. Okay, that final year project will have some motivation, problem statement, aims, objectives, introduction. Then comes how you're going to do that. Then comes why do you do that. Then comes your simulation. Then comes your results. Result based how you then comes. You have to infer. You have to whatever result you got. You need to analyze that result. Then comes conclusion. Then comes reference. This is a process of your whole project. How you're going to do? You're going to do by these four methods. Anyone. Please think from that point of view. Otherwise, it will be difficult for you to understand. Let's say, for example, waterfall model. Okay. Waterfall model. Waterfall model always starts with requirements. Okay, first let's say a project. Why you need that project? Okay, why you need that project? Check it project. when whatever project you will do, directly you will not go to do the simulation, right? You will do first, you will study what is the problem statement of your project. Okay, what is the requirement in the market of your project? What benefit a community will get from your project? All this comes in requirement. So you need to study first. Doing you can do some questionnaire. You can make some questionnaire, Google form, Nalu. You can do some survey. You can do some, like for example, someone last time Pingola group, they did on biogas ke project na bhi. So she was doing a survey. Okay, biogas. Are you aware about biogas? Are you within the community? She was doing a survey, right? So such kind of things you can do. You can inquire, you can investigate, okay? You can interview, and you can form some requirements. Okay, an enemy requirement do dele an enemy an enemy say requirement that comes in requirement. Then according to that, you will build the architecture. Okay, you will build the architecture. Okay, these things should come first. This block need to be comes in the latter part. You'll design an architecture. First designing is going on here. Then after that, coding part will come. Then, okay, in order to do that, whatever the system, the intelligence of the system depends on the programmer's coding. Please note this, okay? What the intelligence, how the system is working, that all depends on the programmer, how he is doing, okay? How the coding part is being done. That means indirectly I can say that the intelligence of a programmer determines the intelligence of your system. So this phase is very important. You can use many things are there. C programming, assembly language, MATLAB for coding. Then you do testing. This is very important, testing. Direct coding, baby, direct result in the, okay, we don't know. We have not tested, so we don't know where it has gone wrong. That's why this testing is important. Are you getting? So testing, okay, if this test, then there will be a problem here. Then last at the end, maintenance, see? Okay, then there is a feedback. See, maintenance, okay, there is a problem here. So it will give a feedback. Okay, you need to change that testing partner, change. You need to change in this coding part. Coding part, you might have to change in the architecture then. Architecture, that means requirement nara change okay. This is waterfall model, but in reality, these things does not happen. That's why this is unrealistic design. So more realistic came, which is spiral model. Spiral model or successive refinement. These are more, realistic. In spiral model, each of these phase, system feasibility, specification, prototype. Okay, first we need to start with system feasibility, whether the system is feasible or not. Then you will do the specification part. Here there is no specification part. See, requirement based have a specification. You need to have the specification of the components. Then you will build a prototype. Then you will make an initial system. Then embedded enhanced system. Each of these spiral will have these three cycle. Like system feasibility will have requirement, test, design. Specification will have requirement, test, design. Prototype will have requirement, test, design. So this is more of a system where the rectification is happening again and again and again in each phase. That's why this is more realistic compared to waterfall model. That thing will happen, right? We won't go back again and change the requirement and again come down in actual scenario. But what we'll do is we'll actually see the requirement of each of the phase in our project. We do this. That's why this is more realistic spiral model. Let's come to successive refinement. Successive refinement is also similar to waterfall model, but here when we are going back from maintenance to requirements, we are going directly. We are not going through build, design, architect, and specify. Are you getting? Test led direct specify na jo. Actually, this makes sense instead of this one. Here, what is happening is, okay, maintenance will go to testing. Every phase na jo mingo bat actually. Direct maintenance na jo, you go to requirement directly. You tell this requirement phase, okay, you need to require this part. This will be changed. Direct requirement na jo, it will change the requirement. Then it will tell the architecture, okay, you change this, you change the code. You don't need to go in each phase again and again when going back, when giving the feedback. That's what is happening here. Directly, it avoids going to each step. Okay, so whatever feedback test has will give to the specify, and what it will change according to its feedback. Okay, so the refined system nalu more it will, that's why it is a refined system. So refined system nalu, it will take the feedback from the initial system, and accordingly the system will be improved. Okay, this is successive refinement model. In a hardware software design model, see, hardware software concurrent in this engineering law, hardware will be, see, there will be requirement specification, architecture, then design. Hardware will be looked after separately, software will be seen separately. That is the only difference in hardware software design methodology. Then we need to integrate each other together, then system test. Separately, hardware will be investigated separately. So hardware will have specification, architecture, design, integration of its own. Software will have specifications, architecture, module design, integration, test of its own. Then they both together will be integrated. Then test will be done. There is no such as feedback here, as here. Another feedback, but here there is no such as feedback. But new methods has come where even in hardware software design methodology there is a provision for feedback. Okay, new things have come, but this is a basic. Are you getting or not? This is same thing as your hardware software co-design. Please see this. This is also, always see power, size, performance, cost. These four we are talking about. So when we are dealing with these four components, okay, we need to have this software and hardware as optimized as possible. Okay, this is to do with design methodologies. Debugger and emulator. Rajesh is telling debugger and emulator. If there is any doubt, you can always stop me. Okay. Debugger will always use to test and debug other programs. Okay, actually, debugger is not a separate hardware. It is actually a software. It's a kind of a program which is installed in a ROM. But these days it has become a tool actually. Now, tool cell of the law, it is not a hardware tool. May please understand this. It is some kind of a simulation tool which we have to use in order to test the program or in order to debug other program. Okay. So test means, after test, of course, you will know where are the errors, where are the mistakes, which has happened in Kale. You must have used in MATLAB also, right? So with the help of debugger, we'll test and debug. Okay, so that your programmers will be, program will be more rectified, or the errors will be rectified. Now, there are three ways to do this debugging. Three ways. In three things we can do. Three ways. Of course, I can say that three ways. One of the ways emulation. Okay, so in a way I can tell that emulator comes inside debugger. That is called as in-circuit emulator. Are you getting? But there is another different note, separate emulator has also come, that is called as system emulator though. See here. So see, debugging can be done. Always remember host and target, okay? Target the host key. So host, always inside host there is a target. Host is kind of a computer. Inside the whatever simulation we are doing, embedded system scenario we are making, that is done by target. So see, debugging has, I told you, three ways to do. One is simulator, one is using target processor, and one is using in-circuit emulator. Okay, see, in-circuit emulator is there. In-circuit emulator takes the place of target processor. What emulation will do is, okay, now emulator, where is that diagram? Yeah, particular, yes, this one. Yeah. See, okay, this is a computer. Okay, there is a ROM here. These two are connected by your microcontroller. Okay, microcontroller RAM interfacing circuits, but important here is microcontroller. Now, this microcontroller is helping to connect this ROM and a computer. This ROM might be a external ROM or an internal ROM. I don't care. Now, what this emulator is doing is, emulator is replacing this microcontroller. Whole of this. System emulator is replacing this microcontroller RAM interfacing circuit. So it will build a system, it will build a scenario whereby you have microcontroller there, you have RAM there, you have interfacing circuits inside. Okay, so that now you are emulating, you are copying something, right? You are emulating this scenario, this block only. So that why we are doing this is because if we are doing originally, okay, taking this microcontroller RAM interfacing circuits, there might be an error and it will be difficult to find that error or erase that, rectify that error sometimes. So that's why, to be in the safer side, we will use system emulator. What system emulator will do is, it will simulate that same environment, and it will try to, okay, there is we can study through this. Okay, the error is here. You can remove this error. say we can do through system emulator. That's why we have this emulator has taken a different scenario. Like for example, these days you are playing games. Okay, let's say games like football games in a PlayStation games, right? In a computer you are playing, or a PUBG games. All those games are there. You are emulating the same environment. When you are emulating the same environment, you're duplicating that environment, and you are creating that environment so that okay, you simulate there. So in a real-time scenario, how it will happen, you will do that. Then you will study that. Then you will apply that in the real-time environment. First, you will study in the emulated environment, a simulated environment. Then you will go for the real original. Then you will apply in the real original. This particular block diagram is original. It's a physical thing. Now, in order to debug this, we will use a system emulator, which is emulating this microcontroller RAM interfacing circuit, so that there won't be errors, so that we can create you can create an environment and we can study about that, we can apply, so that the system becomes more perfect. But what's the difference here between system emulator and ICE? In system emulator, RS-232 port, that is serial communication, is separate. External man. System emulator is only emulating microcontroller RAM interfacing circuits. But in-circuit emulator has included RS-232 serial COM port. Okay, and target system emulating circuit. Chikabe. It's all together in circuit emulator. This is the main scenario. Other things you can see, but the main concept is this one. Are you getting? Any other topics to cover? Other than you can read and you can go through the theory. Like for example, what's the difference between emulator and ICE? What is emulator? What is debugger? You can see by yourself. Okay, you don't have to go that detailedly, but the diagrams are little important. Whenever you are asked to explain this, please, I need these diagrams. Okay, diagrams carries marks, lot of marks, like this diagram, this diagram, this diagram, debugging. Okay. Here, see, debugger also, please understand that there is hardware component, there is software components. Hardware components are separate here, separately. These are software components, and this part is also this AC's part. Hardware, software, both. This can be hardware, software, both. But these days, these are all in a form of program. All these things, I mean, a compile, generate code, RTS, ADAS compilation system, ACs, all these are embedded inside a chip. This is in the form of a chip. All these are in the form of a program, a software. Hardware, separate BMA. Separate B. It goes in a cycle. See, requirements of debugging. There are 3 requirements. Real-time analysis beni denlo, memory substitution beni denlo, and run control beni denlo. 3 requirements of debugging. Okay? Any other topics you want me to cover? Hmm? Okay, so it's not there, then I'll log out. Okay, Tuga, you can always let me know if there are any topics to cover. But embedded system the amchinale over. Now we'll go back to your 8051 again. 8051, there are some topics which we need to cover again. Power control. So okay.
Okay, sir.
Yeah.